I think we can get started with the last talk of this week. We have Amalia and Madden here, and she's going to tell you us about the Piezoaxionic.
Thank you very much. It's a pleasure to be here, and thank you to the organizers for letting me give this talk. So today I'm going to tell you about a new observable to look for the QCD axion that we've called the Piezoaxionic effect. I'm a PhD student at the Perimeter Institute for Theoretical Physics, and this presentation is based on work that I completed together with my supervisor, Asamina Avanataki, and our collaborator, professor at NYU called Ken van Tilburg. So to motivate this, I'm going to tell you about the QCD axion. And then to understand the piezoaxionic effect, I'm going to tell you about parity and time violation in systems of increasing size, so nuclei, atoms, and then crystals. I'm going to tell you about the proposed experimental setup to look for the piezoaxionic effect. And then at the end of this talk, I'm actually going to tell you about a second observable we found more recently, so this is still unpublished, that also uses piezoelectric crystals to look for the QCD axion, but rather than looking for QCD axion dark matter, this is going to be an observable that probes axion-mediated forces. So I told you I'm going to motivate this by telling you about the QCD axion. So as I'm sure everybody here knows very well, we can, in principle, add another term to the standard model, the QCD theta term, that couples to the field strength tensors of the gluons. As I mentioned before, renormalizable, invariant under the standard model gauge symmetries, but violates CP. And this QCD theta term, together with the phase of the quark mass matrices, could lead to a physically observable angle, which would show up in the CP violating electric dipole moment of the neutron. And the fact that we have not yet observed this places very tight constraints on the physical angle theta bar. And as you all know, the solution I'm going to be interested in today is the QCD axion, which also couples in the same way to the gluon field strength tensors and dynamically solves the strong CP problem. And I'm reminding you of all of this because what's going to interest us today is this fundamental coupling, this fundamental coupling of the QCD axion to the gluons. Sorry, let me just check something. Okay, yeah. So we've heard a lot this week about looking for the QCD axion via its model-dependent coupling to the photons. And that so far is where we've had our most success in probing the QCD axion's parameter space. However, today I'm going to tell you about the currently less explored, but coupling of the QCD axion to the gluons, which is actually its fundamental coupling and its model-independent coupling. So since I'm going to be talking about a probe of the QCD axion that depends on its nature as being the dark matter, and also on the QCD axion being very light, I'll remind you of the properties of very light bosonic dark matter. So bosonic dark matter has wave-like properties when its number density in the galaxy is greater than 1 over the de Broglie wavelength cubed. So in our galaxy, that corresponds to a mass of around 1 electron volt. And when this happens, our picture of the dark matter changes from something very particle-like to something wavy and classical. So locally, our axion is a scalar wave that has a frequency that's set by its mass. It has an amplitude that depends on the dark matter density and is inversely proportional to its mass. And there's also a small spread in its frequency. So it has some finite coherence that's set by its velocity in the galaxy, and that's about 1 part in 10 to the 6. And now if your dark matter candidate is really well motivated, you should also have a production mechanism for it. And in this case, we're interested in the misalignment mechanism. So early in the universe, our axion field has an equation of motion cosmologically that looks like a damped harmonic oscillator. And early in time, when its mass is below the Hubble scale, the axion is frozen at the top of its potential. And later in time, as Hubble falls, the axion is going to oscillate around its minimum. And it's these coherent oscillations of the axion around its minimum that have an energy density that scales with redshift like the dark matter, And its abundance today can be determined by its initial misalignment angle and its decay constant. So where are the observables I'm going to tell you about today? Where do they fit into our current exploration of the QCD axion parameter space? So the piezoaxionic effect is going to probe these kinds of masses. So around 10 to the minus 11 to 10 to the minus 7 electron volts. And the ferroaxionic effect is going to look at higher masses between about 10 to the minus 5 and 10 to the minus 2 electron volts. So what is the piezoaxionic effect? And to summarize this observable for you, I've got this cartoon here. So on the left-hand side, we're going to take a piezoelectric crystal. And this piezoelectric crystal is going to contain nuclei that have a spin. And we're going to polarize all those spins in an external magnetic field. Now, if the axion is a dark matter, through its coupling to the gluons, what will happen is it will induce a very small periodic strain in this crystal with a frequency that's set by the mass of the axion. So why a piezoelectric crystal? So what's special about a piezoelectric crystal is that its symmetry structure breaks parity. What that means in ordinary materials is that when you press it, when you deform it, you'll get a voltage across the crystal, and vice versa. If you were to apply a voltage to this crystal, you would see a deformation. And the reason this is happening is because of the parity violating arrangement of the atoms in your crystal lattice, such that when you, for example, in this picture, when you compress it, it will cause an electric dipole moment to form across the unit cell. Now, the kinematics of a piezoelectric crystal are described by something known as its constitutive equations. And they describe how when you apply a strain or an electric displacement to one of these crystals, you can see the effects of a stress and an electric field. So we can understand this in terms of symmetries. So our mechanical variables here, stress and strain, are parity even, whereas our electrical variables, the electric field and the electric displacement, are parity odd. So in an ordinary crystal whose structure doesn't violate parity, these piezoelectric coefficients are 0, and you cannot convert between these parity odd electrical quantities and these parity even mechanical quantities. Now, what happens when we have an axion? So we see here that our axion field is both parity odd and time reversal odd. So we can produce a stress, for example, which is a parity even quantity, by having both a piezoelectric crystal, which gives us some parity oddness, and in addition to having a piezoelectric crystal, we also require some nuclear spin polarization so that we have an extra source of time reversal oddness. Now you can see here that you can, in any crystal, in any dielectric, not just a piezoelectric, also produce an electric field observable from a QCD axion dark matter background. But I'm focusing on the piezoaxionic effect here. The reason being that it's bigger. It turns out that this piezoaxionic effect is going to be something that we can enhance resonantly. And I'm going to show you at the end how these two quantities compare. But for now, we're going to focus on the piezoaxionic effect. Any questions so far? Yeah? Mm-hmm. So this axion here, this is oscillating with time, this axion field. And I haven't got into the details yet, but what I'm telling you is we can already argue through symmetries that we have all of the symmetry properties we need here in order to produce parity even mechanical observables in our crystal. Mm-hmm. Okay, yeah. So summarize again, the piezoaxionic tensor is odd under parity, and can only be present in piezoelectric materials. What we've called this other tensor, the electroaxionic tensor, is even under parity, so it can be present in all dielectrics. But we're going to focus on the piezoaxionic effect today. So how big is this effect? So one way we can understand how this effect comes about is that the QCD axion dark matter, through its coupling to gluons, is going to induce an oscillating nuclear electric dipole moment. And we can imagine that this oscillating dipole moment potential from the nucleus could affect the electrons in our lattice and thereby generate an oscillating stress. Oops, sorry, this is meant to change. Here, so you see as the direction of the dipole moment flips, change the way it changes its potential on the electrons. And now that simple picture has a problem. It doesn't really work. And the reason is something known as Schiff's theorem. So if you were to treat an atom as a system of static and point-like particles, then it turns out that the electric dipole moment of the nucleus is perfectly shielded by the electron cloud. And we can understand this with a picture. So if I give the nucleus a dipole moment, it's going to move its position relative to the electron cloud such that the net dipole moment of this whole system is going to cancel out. Now, you can see that there's some assumptions here, that the nucleus is static and point-like, and they tell you about the ways that you can violate Schiff's theorem. And the way that will be relevant to us in this example is that the nucleus has a finite size. So if you were to do multipole expansion in sort of higher order around an octapole, you get something known as a Schiff moment, which is the relevant parity violating electric moment of this nucleus and is bigger for nuclei that have a larger area. So you can see here, it will ultimately depend on the QCD axion and the size of this nucleus. And then something strange and weird happens, that there's actually some nuclei in nature that are intrinsically deformed in a parity violating way, and they look like this. And if you have a nucleus like that, your Schiff moment is even bigger. It's actually enhanced by another factor of Z. So if you want to make this effect as big as possible, you want to look for these pear-shaped nuclei. And now a little bit of extra technical detail about how the scaling comes about. What's actually generating this effect in nuclei is pion-mediated forces between your nucleons, where one of your pions couplings to the nucleons is actually a parity violating coupling that's proportional to the axion field. So I told you about how we generate this parity violating Schiff moment of a nucleus. And now we want to go from the nucleus to the lattice. So we want to understand how our Schiff moment affects the electrons in our crystal. Now, as we know, a piezoelectric crystal is intrinsically parity violating. And what that means for our ground state electron wave function is that if we consider it in terms of S-like and P-like orbitals, like you would have in the hydrogen atom, that have definite parity, our ground state is actually going to be a mixture of S and P. And now from here to here is quite a technical calculation, and I'm not going to tell you all the details, but I'm telling you the result. That our piezoaxionic tensor depends on how our Schiff moment potential changes. Sorry, the expectation value of our Schiff moment potential in this electron wave function changes as we strain the crystal. And I tried to separate this into two parts. So this depends on your nuclear properties. So on the proton number of your nucleus, on your Schiff moment here. And then this part here depends more on your material properties, so the volume of your unit cell, the number of nuclei with large Schiff moments in your unit cell, and here how your fraction of S and P orbital change as you strain the crystal. Now this part here, this has been the most tricky part for us to calculate. We believe it's order 1, and we have some naive dimensional analysis type estimates for this quantity in our paper. And we believe also, based on its symmetry properties, that it should be related to how strongly piezoelectric your crystal is. However, that our estimates for this at the moment, honestly, are not quite precise enough, and we believe that you would need to use density functional theory to improve this factor here. And that's something that we hope we might be able to find people to help us with in the future. So now we have all the information we need to think about what the how big an equivalent strain in this crystal would be from an axion. So if you remember, a strain is this dimensionless deformation of the crystal. It's related to our piezoaxionic tensor, which, as we now know, depends on our Schiff potential and also on how strongly piezoelectric our crystal is. It depends on the stiffness tensor of our crystal. It depends on the nuclear spin polarization, and it depends on the axion dark matter. Yeah, the axion dark matter. And we think the size of this is around 10 to the minus 26, which sounds really small, but I'm going to tell you why we think that's achievable. So now I'm going to introduce the technology, so resonant mass detectors. So these were used historically. The first example that I know of is the Weber bar. So Weber here in the 1970s was trying to find the strain produced by gravitational waves. So he made these huge meter-sized bars of aluminium. I think he actually tried to read it out with transducers that were based on piezoelectric crystals. And he unfortunately didn't manage to see gravitational waves. His strain sensitivity was too low. But more recent incarnations of this idea are experiments like Auriga, Nautilus, and Minigrail. And actually, when we look at their strain sensitivity to scalar waves, we can see that they reach around 10 to the minus 25. And now more recently, Michael Tobar and his collaborators in Australia have been looking at detecting high frequency gravitational waves using these small quartz piezoelectric crystals that have extremely high quality factors. I think I've had numbers of something like 10 to the 12 for these. And they can reach, at the moment, low strain sensitivities around 10 to the minus 22. So we think this points to us and says that this is achievable. So what's the experimental setup that we have in mind? So first of all, we want to find a piezoelectric material that has very low mechanical noise and very big shift moments. Then we want to cool this material to millikelvin. The reason being that cooling it to millikelvin will reduce our thermal noise, and it will also allow us to achieve higher nuclear spin polarizations. And then once you do these three things, you should hope that if the dark matter is the QCD axion and it's in the right mass range, that it will cause a strain in this crystal. And because this crystal is piezoelectric, when you strain it, you generate a voltage. So ultimately, you'll have a very small alternating current in the circuit here that you can measure out using a squid. I'll just stop for any questions again if anybody if everyone's following, I'll carry on. Yes? Mm-hmm. So they're using quartz, and quartz is a single crystal, and they can grow to very high purity, and it's very well understood technology. And beyond that, they can also cool it quite low that increases the quality factor. And beyond that, I suppose there might be some element of luck there. So I should say, I told you that quartz has really great quality factors, but actually quartz is not the crystal we need. The reason being, quartz doesn't have a nucleus with a big shift moment. So it's not going to make our piezoaxionic effect as big as we would hope for. And so that means we need to look for a new material. I should be clear, at the moment, we don't know what the ideal material is, but we have ideas about how we could look for it. So first of all, piezoelectrics are actually a really big class of materials. They make up about 20 out of all 32 possible symmetry groups of crystals. Yeah. Mm-hmm. So the best answer I can give you is that I can point you to the literature of this group in Australia, where they have tested cooling these crystals down to cryogenic temperatures and looking at their quality factors, and they see that they're very high. Mm-hmm. So as I said, we need a high density of nuclei with large shift moments. We want good acoustic properties, so a high Q factor. We want strong piezoelectric properties. And then finally, if we're going to look for a new material, then it might help if it has some structural similarity to something like quartz so that we know how to work with it. So one way we thought about doing this is we've gone onto this database called the Materials Project. And there you can find crystals that people have already grown in the lab. And we can look at their symmetry classes to check if they're piezoelectric, to check if they are structurally similar to materials that have already been grown and used, for example, in mechanical resonators. And we can check that they have a reasonably high density of a nucleus that has a high shift moment. And for example, here I've mainly used examples of materials that have uranium and dysprosium. So uranium-23 has an isotope 235 that is pretty stable and is octopole deformed. And dysprosium here also has an isotope that's stable and octopole deformed. So how do we scan? So the difficulty here is that we are most sensitive when we match the natural frequency of our crystal that's set by its size to the frequency set by the mass of the axion. And you can only grow so many crystals. So how do you scan in between? And that's a difficult problem. So apart from the idea that we would grow some kind of xylophone of crystals of different thicknesses, the other thing that we believe we can do is we can tune a little bit in between these crystals by varying the electrical response of our system. So in our circuit here, this part here, I feel like showing this to you because there's so many experimentalists here. So this part here is the piezoelectric crystal that we've written as an equivalent RLC circuit. Here we have an impedance matching stage and a squid readout. And as you can see here, we have an external RLC circuit. And the idea is that we can tune this RLC circuit, and that will tune the electrical response and the electrical resonance frequency of our entire circuit. So this is limited, but it does give you some potential to scan. So backgrounds. So one important background for us would be things that give you a fictitious voltage signal. So that could be fluctuating nuclear spins, and we calculated this and we found that it's a small effect. Or it could be fluctuating magnetic impurities, and we found that that would need to be below parts per million, which we believe is fine because we've found examples that crystals have been grown with impurities at lower than parts per billion. Vibrational noise, this is a systematic that's already been demonstrated at experiments like Auriga. So that leaves us with an experiment that we believe will be thermal noise limited. And in addition to thermal noise, this thermal noise would be generated by the crystal and also by the squid. So here is an idealized forecast for an experiment. So if it's too small, I'll tell you what these axes are. So here's the axion mass along the bottom. Here is the inverse of the axion decay constant, and here is the frequency. Now this yellow shaded band here, we think is the overall reach that an experiment like this could achieve. And now these two patches, these two areas here, this blue and this red, correspond to two different experiments based on the size of your crystal. So here you would have, for both of these, you have the same volume of material. Here you have 13 crystals of different thicknesses, where the thickness is ranges from 4 to 2 centimeters, and we're going to displace them logarithmically in thickness. And its longest side would be about 40 centimeters. So we think that's about as big as you could grow a crystal. And it would have a total integration time across all of these crystals of about 10 years. And all of these little fluctuations here, they correspond to when you're hitting the fundamental mode of each crystal. The same here. Now, this is for a smaller setup. So now in the same volume, you can have 128 crystals. Again, we would have 13 different sizes and a total integration time of around 10 years. And we believe that that would be necessary to reach the QCD axion line. I mentioned earlier that we're interested in the piezoaxionic effect because it's bigger than the electroaxionic effect. And here is the line for the electroaxionic effect. It's not resonantly enhanced, and it's above the piezoaxionic effect. Just to be clear on this side here, so I said that we cut off our experiment where we believe that the crystals would just be too large. And on the other end, we start to lose sensitivity due to our squid. One more comment here, because it's been brought up in the past. So we really want to reach the QCD axion line because when you're looking at the coupling of the axion to gluons, the parameter space above the QCD axion line is actually less well motivated because it requires a fine tuning in the mass, so the first and second derivative of the potential.
Did I hear correctly that the magnetic noise is subdominant?
Yes.
Is that because you have a small sample?
Well, yes, I suppose if you made your sample big enough at some point, it would become important.
I know for actually, probably that if I have a small sample, then I'll have a large slip reflection or magnetic. But it's not happening here.
I think I'm going to check the scaling for you when I'm done, and then tell you. Okay.
Yeah.
So one target that we could look for before we look for the QCD axion coupling to gluons, as we know that's quite difficult, is we can look for this model-dependent coupling of the axion to electrons. Now, this has some advantages. If you look at this operator, so when we take the non-relativistic limit of the axion coupling to electrons, we find that this operator here is p odd and t even. And if you remember, nuclear spin polarization was a t odd quantity. So the fact that this is t even has the advantage that we don't need unpaired electrons in this system, and we don't need the electron spins to be polarized. We also can use a material that's more readily available, seeing as we no longer require big shift moments either. And we believe that this, using the same setup as I told you before, can already, could potentially be below white dwarf cooling bounds. Sorry, I'll mention one more thing, one more detail. So if anybody's wondering what's happening here, we've actually considered 2 different possibilities for the thermal noise of the squid. One of these is when we reach the standard quantum limit, and one of them is a present-day squid. So future directions. We want to do more precise shift moment calculations for stable octopole deformed nuclei. And that's actually something that we're already doing with a professor called John Engel, who's a nuclear physicist. We want to do density functional theory calculations for the piezoaxionic and electroaxionic tensors. And we want to do more experimental investigation into suitable materials. So now I'll tell you about the ferroaxionic effect. But first of all, I'm going to tell you some history. So in 1880, the Curie brothers discovered the direct piezoelectric effect. So this was that a stress produces a charge. Now in 1881, so a whole year later, somebody called Gabriel Lippmann predicted the converse effect from thermodynamics, which was that a charge produces a stress. And then the Curie brothers verified this experimentally. And the reason I'm telling you this is because a year after we found out about the piezoaxionic effect, we realized that there was also a converse effect. And as you heard yesterday in Andy's talk, we've called this the ferroaxionic effect. And the idea is the following. We now have a piezoelectric crystal. Its nuclear spins are polarized again, and it can source an axion-mediated force. And that axion-mediated force is going to interact via the axion coupling to nucleons to a spin sample. And this is going to be an NMR type experiment. So we're going to move this piezoelectric crystal at the Larmor frequency of the NMR sample in order to get a resonant enhancement. So the axion in this instance, we're interested in a monopole dipole potential. So the axion is going to have a scalar coupling generated by the piezoelectric crystal. And from the perspective of our NMR sample, this is going to look like an effective magnetic field since it interacts with the spins. So how do we understand this in terms of symmetries? So we can think about the Klein-Gordon equation for our axion field, where our axion is sourced by the scalar coupling to nucleons and some density of nucleons. And this scalar coupling is related to the atomic number in your crystal, the axion decay constant, the Schiff moment, the nuclear spin polarization, and this atomic matrix element that was related to how you mix your Schiff moment potential with the electron wave functions. Now, why we need a ferroelectric crystal is the following. So this atomic matrix element, which is parity odd, is a vector and it needs some direction. And for the piezoaxionic effect, we already had a direction in our system that came from the strain. Whereas now we need something to give this some direction. And we get that from the ferroelectric crystal because inside a ferroelectric, you have some direction for your electric polarization. So I think Andy showed you this last time, yesterday, in fact. The idea is that we're going to have a spin polarized source mass. We'll move this at the back and forth at the Larmor frequency of the NMR sample. Here you have a superconducting shield, so that will block all real magnetic fields, whereas the axion, which isn't a real magnetic field, will be able to pass through this unaffected. And find it so when you move this at the Larmor frequency of the spin sample, it will cause some magnetization of your spin sample that can be read out with a magnetometer. Now, one confusion I heard yesterday was that people were trying to understand how you would tune this frequency here to scan the axion. What actually determines your sensitivity to the axion is this distance here, so the range of your force. And you determine the Larmor precession frequency does not depend on the mass of axion that you're sensitive to. So here's a preliminary plot. So we've used uranium-235, and we've considered two different setups of different size. So one has a separation of about 0.15 millimeters, and one is about 1 millimeter, an integration time of a year. Yeah, I think that's all I've got to say about this plot. I've actually gone so fast, I've got plenty of time left. So in summary, to tell you about these two experiments. So both of these experiments were looking for the fundamental coupling of a QCD axion to gluons. So we're looking for the GG dual coupling. For the piezoaxionic effect, we can also use the setup to probe the axion coupling to electrons. This, I said, was sensitive to a mass range between 10 to the minus 11 to 10 to the minus 7 electron volts, and this had to be the dark matter. Whereas for the ferroaxionic effect, we are always probing the axion coupling to gluons, but we also need another coupling to nucleons at the same time. So we're probing both of them together. But this is interesting because since you require the axion coupling to gluons, you always know that you're probing the QCD axion. And this would probe a different mass range between 10 to the minus 5 to 10 to the minus 2 electron volts, and this wouldn't have to be the dark matter. So the QCD axion dark matter can excite vibrational modes in a piezoelectric crystal via its model-independent coupling to gluons. Ferroelectrics can source QCD axion-mediated forces that can be detected using an NMR sample, and this would be complementary to cavity experiments. Yeah, I went so quickly, I've got plenty of time. Thank you. Yeah. Yes. So in Ariadne, what they have is they're rotating the source. So they have this configuration with like it looks like cogs, like a gear, exactly like a gear, yeah. That wasn't ideal for this setup. So now we're just using, yeah, linear motion, yeah. Yeah. Okay, so actually quartz has a piezoaxionic effect as well. It's just that the piezoaxionic effect is small because it doesn't have a nucleus with a big shift moment, but it is there. Whereas an electroaxionic effect, you actually don't even need a piezoelectric crystal that would be present in any dielectric. I did speak to Tobar at one stage about a year ago, and he's very interested. I think the first thing that he could do is he could look for the axion coupling to electrons, since you could do that with quartz. So that's the status of things.
Question. So just like before, it's like it's important to push that band, and because the reaching back is not very well motivated. So once you reach that band, does it make sense to push to below that sensitivity, or is that?
So yeah, actually, it's easier to build a model that goes below the QCD axion line, but then it's also technically more difficult. So. So they're not the same effect. So actually, both of these things depend on the shift moment. So in Casper, they're looking for an NMR type effect inside this crystal. And one of the interesting things about this experiment compared to something like Casper is because they're looking for an NMR effect, they're probing, let me go back a bit. So if we go back to these problems of fluctuating nuclear spins, because they're probing the NMR frequency of their crystal, their biggest noise source, I believe, is to do with issues of noise from fluctuating nuclear spins. Because we're not probing the NMR frequency of our crystal, magnetic noise is not such an issue for us. So that would be one comparison between our experiment and Casper. Well, for one thing, we're looking for an oscillating effect. That's the first thing. Second of all, you could run this experiment twice. You could polarize the spins and see if the effect persists when you turn off the polarization, which I don't know if that would happen in your example.
One of the slides that the upper bound was
Maybe that's not something we've thought about. We've only considered this setup here. So if you have an idea about a setup that could probe higher frequencies, then we would be very interested to hear about it. Yeah, I believe that's the main limitation there. Okay, let me go back there. Yeah. So this whole yellow region, that would be very difficult. So you see each of these setups here. So over all those crystals are the total integration time of 10 years. And by both of those setups, I mean the blue and the red. So to cover all of this, that would be tricky. And what you would probably need to do is think of a way to mechanically scan. By mechanically scan, I mean the fact that we can't change the mechanical resonance frequency of the crystal without changing its dimensions. If you can find a way to overcome that obstacle, for example, maybe you can mechanically load the crystal somehow to change its resonant frequency, then more of this parameter space might open up to you. But what I've shown here is all the parameter space you could probe with this effect, but it would be difficult. Mm-hmm. Yep. Mm-hmm.
The rate of change is slower than the speed of sound in the computer. I'm just curious. That's how I find this effect. My kind of visual picture is essentially you're forming the crystal, but it's formed slowly enough that it's able to just itself.
Possibly. I mean, I can't remember the numbers off my head, but I think we would have seen that. We would have seen that if that does happen here.